He's been with the Arctic Institute since 2016, and he's been a postdoctoral scholar, and he's now transitioning into project manager for our CFI, Canada Foundation for Innovation, and our CCADI grant. So he's herding that large group of researchers and everything. So please welcome Dr. Ravi Shankar.
Thanks, Mel. Well, good morning, everyone. Like Melanie said, my name is Ravi, and I am a scientist with the Arctic Institute of North America. And today I'd like to speak to you guys for the next 10 minutes or so on models and how we can use models and their predictions to inform the future. And by the future, I mean essentially adaptation initiatives as well as mitigation strategies to deal with some of the near-term effects of climate change. One of the study sites that we've been looking at for the last 2 years at the Institute is Sax Harbor. So I'm going to be focusing on the changes that we've been seeing over the last 60 years in this region. So I'd like you just to take a couple of seconds and digest this picture. You've probably seen this picture this year. And imagine the Arctic, let's say 20 years from now, 30 years, 40 years. And I've got maybe 2 questions or 3 questions to pose to you. What changes do you think we'll see in the Arctic in the next 10 years, in the next 15, maybe in the next 50 years? What thresholds do you think we might pass in this region as a result of these changes? And like Maribeth just said, how might these changes actually reverberate around the globe? And I'll be honest with you, I've thought of those questions. I have no answers for them, really. Sorry to disappoint you. But the truth is that this picture, as I look at those questions, those are challenging questions to wrap my head around. But this picture of a melting Arctic is not one that's photoshopped. It's one that was taken this year. So the Arctic as we know it, and as we've just heard, is changing. There is dramatic, rapid, unprecedented changes taking place in the Arctic. And again, Maribeth just did a fantastic job of going through some of these changes, but I'm just going to reiterate it. We're seeing rapid sea ice loss. We're seeing increased melting, for example, of the Greenland ice sheet, and much of that displaced water is acting as a catalyst to global sea level rise. What we're also seeing is rapid Arctic warming. We know that 2018 was the second warmest year in the Arctic. And we also know that the Arctic is warming approximately 2 times higher than the global average. And therefore, there is, of course, a trickle-down effect because of these different scenarios. What we're seeing is landscape changes as a result of this. We're seeing, like Maribeth just said, increasing frequency of wildfires. We saw what happened this most recent summer in the Yukon. We saw what happened, for example, near Delta Creek in Alaska in July and August of 2019. Coming closer to home in terms of the coastal zone, what we're seeing there is rapid coastal erosion. We're seeing permafrost thawing, and we're also seeing, most unfortunately, increased hydrodynamics. It's a long, fancy term, but essentially all it means is that we're seeing increasing amplitude of the wave activity at the coastline. So what's happening, for example, is if we have very minute or very small increases in global sea level rise, it just acts as a base for storm surges when those storms happen to propagate further inland, and that can cause significant flooding as well as coastal erosion. And of course, that can lead to the loss of the environmental and cultural histories of many of the people that occupy this region. So like I said, we're seeing these dramatic, we're seeing these rapid changes, these unprecedented changes. And the sad thing is, these changes that you're all seeing here have really taken place within the last 30 years. So what does this mean for us? What does this mean for the next 30 years? What if we had a crystal ball that we could look into the future? What if we could actually peer into the future? Taking it a step further, what if we had a virtual world that we can predict some of the changes that might happen in the next 5 years, 10 years, 20 years? And this is a picture that my 4-year-old son colored for me last week, and I thought I'd put it up there because I think as scientists, it's important that we recognize that we are sentient human beings. What are we leaving? What kind of world am I leaving for my son 20 years from now? He thinks that his daddy actually works with polar bears. I'm not going to be the one to disappoint him, but even this species is under threat. Like Maribeth said, like Melanie said, we're seeing young people standing up even as we speak, massive marches that are taking place. We saw a 16-year-old, Greta Thunberg, on Monday, someone that's passionate. And it's important that when we use models, we actually create a virtual world that we can actually give them some robust scientific data that will facilitate planning, that will facilitate maybe even future relocation for some of these communities. So, can we create that virtual world? In short, the answer is yes. So for a while, we've been using these comprehensive Earth system models, just a fancy term for what's referred to as climate models. There are several different types of models that we use. We use global models, regional models, as well as local models. At the Arctic Institute, we are essentially using local and regional models. Some examples of those models are hydrodynamic models, sediment transport models, which look at erosion and accretionary processes. But these models are based on sound science that we have actually been conducting for centuries. They're based on physics, of course, and they really allow us to assess how the choices that we make today, the drivers of the climate essentially that we are modifying as human beings, how those choices are going to impact the future. So at the Arctic Institute, one of the things that we are looking at, and as a coastal geologist, a geomorphologist, one of the most significant components of the coastal zone is, of course, the shoreline. Brian may disagree with me, but the shoreline, essentially, understanding where the shoreline will move. The shoreline is simply defined as that dynamic terrestrial marine interface. And understanding where the shoreline will be 5 years, 10 years, in fact, 5 months from now, it's important because we need to establish aggressive mitigation strategies to deal with the effects of climate change. These are some of the drivers that we incorporate into our models whenever we're looking at modeling the future scenarios, for example. And those are all catalysts for shoreline change. For example, we have biological processes. This is an example of bioclastic sediment production, a major driver of the change. We have hydrometeorological factors, things like sea level rise, storms, winds, all of those different scenarios. We've got external geodynamic processes, weathering, sediment transport. A big key in any model that we run is, of course, human-induced activities. So anthropogenic actions. Are we nourishing our beaches, for example? Are we dredging the near shore? These are all significant. And of course, within the context of Canada's north, there's what is referred to as internal geodynamics, because we know at some point in time in the north, glaciers cover this region, and as those glaciers have melted, the Earth's lithosphere is now rebounding. So isostasy. So vertical ground movements is a fundamental driver of change, and it must be considered when we're running our models. So during this study, one of the objectives of this study was in speaking with the elders of the community. They wanted us to assess what is the current morphology, what are the current rates of change for their shoreline along Southwest Banks Island, but specifically where the community resides in Sax Harbor. In obtaining those rates of change, we were then able to use a model to provide a visual as well as a quantitative forecast of the shoreline 47 to 50 years from now. And then we used another model to quantify the physical vulnerability of those areas to the near-term effects of climate change. The region that we looked at is the community of Sax Harbor, where you see the star represented, and it's located on the southwest coast of Banks Island in the Northwest Territories. As of the most recent StatScan census in 2016, the population is 103. When I mentioned this to some of the elders in this region, they laughed at me because at any one point, there are at least 700 to 1,000 people living there. There's a fundamental distrust whenever a census comes around, so they just don't complete it. The study area that we analyzed is approximately 44 kilometers in length, all the way along shore, moving from Sax Harbor, where you've got the presence essentially of the residential structures and the airport runway, transitioning all the way west through Martha Point, an area that's referred to as Duckhawk Bluffs, and then ending on this end at Cape Collect. That Cape Collect region, we were asked specifically by the community to analyze it. It's what is referred in geology or geological terms as a spit, which is an elongated body of sand. We did do the analysis. I'll let you guys know what we found in a second. But in terms of the geology, it's dominated by unlithified coastal bluffs. So you've got the presence of loose, uncompacted sediment, which acts as a catalyst to change. It's also a low-energy environment, so it's microtidal. Tidal ranges are in the region of 0.7 to 0.9 meters. And it's a very varied geology. So you've got things like silty sand horizons and segregated ice lenses. I see some people actually falling asleep with geology, so I'm going to stop there. But essentially, the geology of any area really acts as a fundamental driver of change. In terms of the data that we've been able to collect at the Institute, I'm making a plug for the Institute here. This database of shorelines for Sax Harbor and for neighboring regions, we are pretty proud because this is one of the most comprehensive database of shorelines for the region. The mechanism of obtaining these shorelines is predominantly from Landsat satellite imagery. Now, there are approximately 3 major reasons why we're using Landsat. The number one reason is that it's free. We pay nothing for this. Secondly, the spatial coverage is much greater, so you're able to now analyze a much wider swath of an area as opposed to actually being on the ground conducting a high-resolution topographic survey. And of course, the sample frequency is much higher. So you're able to analyze change from a single data source. So it means that maybe a student who's listening to me talk today, 10 years from now, they'll be able to take these shorelines and then rerun this analysis and to see how has this area changed. So those are some of the advantages, the inherent advantages of using Landsat. But there is a mechanism by which we're able to extract those shorelines from Landsat imagery and follows a methodology that was developed by the United States Geological Survey in 2017, in which they're able to essentially obtain these red lines. And it goes through a process of histogram thresholding, band ratioing. I'm happy to have a conversation with you if you'd like at coffee break, but it's really tedious in terms of the methodology to extract that shoreline. But Landsat 8 Band 7 has some really good advantages because you're able to essentially distinguish between the reflectance of land and water. So that's why you're able to get those red lines. Now, in terms of the model that we've used, I'm not going to spend much time speaking about the model, only to say this. The model is one of the newer ones that is in existence for analyzing shoreline change. It really builds on a lot of the advantages of DSAS, which is referred to as Digital Shoreline Analysis System, which a lot of people across the globe are using to analyze shoreline change. One of the great advantages of this model is it does this. On areas where you have curvilinear or sinuous shoreline segments, generally what happened prior is that you'd have transects that cross one another. And as those transects cross, it tended to usurp the rates of change. So as a scientist, we are providing rates of change to coastal planners and policymakers. We want to ensure that when we tell them that, hey, your shoreline is eroding at such and such a rate, that it's something that they can take to the bank. So in using this model, we've gotten rid of some of the uncertainty of the estimates that generally have been provided for studies like this. So let's get to the results. The first thing that we did was to analyze the change along the entire coastal segment of Banks Island. So over a 60-year period, as you can tell by looking at these pink or reddish boxes, there are 2 distinctive erosional hotspots. So in the region where the community is living, everything that's below 0 specifies or signifies erosion. Everything that's above signifies accretion. So where the community is residing in Sax Harbor, the shoreline is eroding. As you transition further west to Duck Hawk Bluffs, that is also eroding. And there's a reason why I'm pointing these out, because it's one of those regions that they are already considering for possible relocation. But as it turns out, the model is telling us that might actually not be a good idea because it's showing signs of erosion. Over the entire period of the study, the overall mean rate of change is madly positive, which is telling us that the shoreline is in a state of dynamic equilibrium. If you look at these 2 boxes here, it's telling us, well, the erosion and accretionary processes are balancing out one another. So not too bad. What has happened, however, in the last 20 years is something that should concern us, because the overall mean rate of change is now negative. It's negative 0.39. And what's also happening is that the percentage of the shoreline that's eroding is no longer 50-50. It's now 75% eroding and 25% accreting. So something is happening. We were then asked to, of course, consider what's taking place specifically where the community resides, so Sax Harbor. Again, over the long-term period, the entire length of the study, over 60 years, what we found, overall mean rate of change is madly positive, so 0.04. Again, percentage of eroding transects and accreting transects are pretty much balancing out each other. So not really too much of a cause for concern. But when we fast forward to what has happened in the last 20 years, the results are startling. It's telling us essentially that 90% of this shoreline that's fronting the community is eroding, and 11% essentially is accreting. This accretionary signal, unfortunately, has to do with the geology. It's a depositional area, and there are not many houses in this region. So this may actually serve as one of the best hopes to relocate the community. So in terms of using those rates of shoreline change, we took it a step further. The model also allows us to keep things as is, which is what we did, and we just put those rates of change in, and then fast forwarded, based on a linear trajectory, what may happen 50 years from today's date. Unfortunately, it's telling us that the alongshore segment along Sax Harbor, and you can see the purple line is telling us the 2015 shoreline, where that shoreline was, and the red line is telling us where the model thinks that the 2066 shoreline will be. It represents an increase in the rates of erosion. It looks mildly here, mildly more, so 0.49 as opposed to 0.47, which is telling us that this is something that should be a cause for concern. Finally, we used a model that's referred to as AMBUR-HVA, a hazard vulnerability assessment. It really just gives the community and coastal planners, policymakers, an idea of what are the most vulnerable shoreline segments to the near-term effects of climate change, and pretty much exactly what we thought in the region of Sax Harbor, as well as you transition further west, Duckhawk Bluffs. Let's forget this Cape Kellett spit, that no one can literally actually reside there because it's ephemeral, it's changing to and fro. But the most positive news that we have is that there is this 3-kilometer area that defines the intersection of Sax Harbor and Duckhawk Bluffs, where you can actually think about possible relocation. As Maribeth said, relocation is not something to be taken lightly. You're looking at millions of dollars to relocate a community of 103 people. But the mechanism of sediment transport here is why this area is actually accreting. You've got 3 mechanisms of sediment transport. Again, I'd love to have this conversation with you, if you so like, during the coffee break. So to conclude, there are a variety of mechanisms for coastal erosion: increased wave activity, storm events, decreasing sea ice extent, coupled with smaller things like thermal ablation and regional submergence. The take-home story, if you remember nothing else about this talk today, is that over the short term, over the last 20 years, 2 things are happening. The rates of erosion are increasing, and the spatial extent of erosion are also increasing. So much more of the shoreline, much more of the alongshore length of the shoreline is now showing us signs of erosion. It worries us because if we start messing with the model and we start tweaking it to show us an increase, for example, in storm intensity, those are only going to work as catalysts for even more shoreline erosion. So with that, I'd like to acknowledge the co-authors of the study that we have in review. And I'd like to make a plug for the work that Dr. Matthews, who's also with the Institute, has been doing. She has developed a story map, an ArcGIS story map, which really is now a good way in terms of telling the community some of the changes that's taking place, as well as informing policymakers. So with that, I know I've gone over my time, but thank you very much. I'm happy to take any questions at the break. Thank you. Thanks, Marc.
Okay, thank you, Dr. Sankar, and I'd like to welcome to the stage Andrew Applejohn, who is the Senior Science Advisor for the Northwest Territories.
Thanks. And good morning, everybody. I know especially the early career folks in the room are going to be really excited to hear about science policy. Try to contain yourselves. I'm happy to be here this morning, and thanks, Mary Beth, for inviting me. I was in town on other business, and I have to run out to catch a plane about 1:30, so it doesn't mean I don't want to talk to people over lunch. I do, very much so. And my contact information is going to be the last slide. I do encourage people, particularly those folks who intend to work on programs in the Northwest Territories, to get in touch with myself or my colleagues within the GNWT. We'd like to hear about your plans. So I am going to talk a little bit about science policy. The governments of all 3 territories have taken steps to address research priorities in their own territories. We were the first. Not for any particular reason, I guess, other than I was looking for a different job. So I'm just going to talk about what our knowledge agenda is. I should have another line in here, which is why the knowledge agenda. Why is it useful? Why is it useful to people in this room? Why is it useful to people who work for the government of the Northwest Territories? Why is it useful for the residents of the Northwest Territories? And how will we implement our science policy? The Northwest Territories as a jurisdiction, and this goes back to pre-division, really relied on Canada for all of our science. The science agencies of the government of Canada, over decades provided exemplary, world-leading Arctic science. Canada really focused on building capacity in the north. They trained lots of young scientists, moved them to the north. They lived there. They trained northerners. They invested in wonderful infrastructure like the Inuvik lab, which used to be my lab, field stations, infrastructure associated with national defense. A lot of the big investments you see associated with Arctic science in this country were associated with ships, big red ships, not gray ships, big red ones, and industry. Some of the biggest periods of investment in Arctic science in our country were associated with the energy industry or associated with mineral extraction. And we were just talking about Kuluk. I'm glad I had a picture of it here. But what did that do for Northerners, and how did that relate to GNWT and the other territorial governments as Canada backed away from Northern science? It didn't leave us in a great position, frankly. For territorial governments to rely solely on Canada to provide the information we need to make decisions, when Canada left the building, we were scratching our heads. How do we influence the decision-making in Ottawa now that Ottawa is no longer in our territories? They've retreated to Ottawa. How do we do this? Well, we start with policy. And in the Northwest Territories, we started when we first took a little bit of responsibility for Northern science, back at the sort of the dawn of our legislative frameworks. Back in 1974, we established something called the Scientist Act of the Northwest Territories. It replaced something that Canada called the Explorers and Adventurers Ordinance, which in a nutshell summarizes Canada's attitude toward science in the north, but I don't have enough time to talk about that. That's why you need a permit when you come to Nunavut or the Northwest Territories to conduct scientific research. You need to get a permit from us. Also in the Yukon, they went a different path, but Nunavut and NWT are pretty close in terms of their legislative requirements. In 2009, we produced something called the NWT Science Agenda, where we laid out a framework for establishing a set of priorities for our government and a policy foundation that says we're no longer just the consumer of research information. We are a generator, we are a promoter, we are a regulator, and a user. So that was the first step in 2009. We revisited the science agenda in 2017. The knowledge agenda was the result, and now we have the knowledge agenda action plan that pretty much ruined my summer, but that's a different story. Those are the two documents. I almost had a picture of the action plan, but I don't. I have a few hard copies of those I'll throw up at the front desk. The knowledge agenda, that is. So what is the knowledge agenda? Really, we took the science agenda and we thought about it a little bit and thought we really put an emphasis on hard science, hard environmental and ecological and human-focused science. And we didn't put enough emphasis on the fact that people that live in our territory that don't identify themselves as scientists still possess a great deal of knowledge about their environments, about their communities, and about technical solutions to problems that exist now. So I can say that I was very lucky in the mid-2000s to run a very large science program in the Western Arctic. We spent about $67 million in 4 years. We spent 93% of that on Inuvialuit businesses. People that live in the Arctic are very good at doing what they do. There are lessons to be learned from people who live day to day in the communities that you're going to study in. You should talk to them. You should learn from them, and you should build your programs around what they know. That's why we have a knowledge agenda, not a science agenda. There is more than one way to skin a cat, and don't think because you've spent a lot of time in a lecture hall, you know any more about technical aspects of northern life than people who actually live in the north. And we recognize that in our policy format. Anyway, we use this document basically to come into rooms like this and say, these are the things we need. We're a small government with a huge geographic land base. There's 42,000 people in our territory, over 1.2 million square kilometers, if you don't count the water. And we develop the facts we need to make decisions largely based on partnerships with academics, with regional governments, with federal governments, and increasingly with international governments. So we use this to attract attention to issues we need to have people work on. So we'll talk a little bit about the core research areas we've identified. I could go on for a couple hours about these if we break them down into detail. I just walked out of a meeting last week where we identified 188 new priorities specific to wildlife. So I'm going to gloss over those. I'm going to say cultural sustainability. This really means people, culture, what's changing, language, traditional knowledge, sense of community. We know there's specific research outcomes we want to see addressed there. Heritage resources, archaeology, they're all outlined in that section. Environmental stewardship is the catch-all for all of the environmental information, water, wildlife, biodiversity, and change related to those things. Health and wellness is the people-focused one, and the interrelationship between environmental health and human health. Natural resource management is about finding better ways of delineating natural resources as well as exploiting them in a responsible way. And sustainable communities catches a whole bunch of things. That's economy, that's community wellness, that's sustainable energy systems, that's civil infrastructure, and really the business of providing government services to communities in a way that's sustainable. There are cross-cutting themes identified in the agenda. All 5 of those pillars are deeply impacted by climate change. We recognize that. We know that this is going to be a driver. As a government, we are capable of delivering services to our citizens, but we recognize the way we do that is going to change because of climate-related pressures. We know that the way we conduct research, the way we monitor, the way we count, the way we deliver services will change in response to changing technology. And we sincerely hope that the way research is conducted increasingly will involve northern people directly. And that's, if I'm going to spend any time, it's on that. We know that, and I think Mary Beth touched on some of this earlier, in the past, the junket-based science, the quick in, quick out, has been a popular way to address academic priorities. It's been a popular way to address priorities expressed by federal governments as well. But I think it's a much better investment for, particularly for early career scientists, to make that investment in people, connections, and communities. You'll wind up with better science, you'll wind up with more effective partnerships, and you'll wind up with a better career, a career that actually impacts the communities that you say you're serving. So why is an agenda useful? Why is articulated research priorities something that we strive for? Well, largely because we were told to. Canada pointed out to us that we shouldn't just complain. We shouldn't just, show up at funding allocation meetings saying you're missing it, you're not hitting our needs, even obliquely. So we did. We started to write things down. So we hope we have clearly articulated in broad terms our research priorities across all departments, and it's really fun to get people from infrastructure and health and environment in a room and talk about who's got the greatest priority. It's why it takes years to do. We're trying to focus effort to bring together research programs that make the most sense in the northern context and are in the interests of our people and our communities. It provides a strong foundation for research partnerships. I can tell you right now, I write a lot of support letters for grant proposals, large and small, and if you can't find a way to identify a specific target in our science agenda or a knowledge agenda or a plan articulated by one of our departments, I don't write the support letter. We have expressed our needs. It's up to people who are seeking funding support to find a way for your program to meet our needs. Okay, so we'll just move on here. So we have an action plan to support our knowledge agenda. I just checked to see if it was actually online, and it's not. So I think I know that it's supposed to be there in July. It was, but like I said, it kind of ruined my summer, so it's not there yet, but it will be soon. I encourage you to go to the GNWT website, look it up. But it really outlines in great detail, excruciating detail almost, how we're going to articulate some progress under the knowledge agenda. And it really focuses around building better research within our government, collaborating with external partners like yourselves in ways that engage communities and encourage maximum participation of NWT residents, and increase the impact of the research. And that's really about communicating what you're doing and what your results are back to the stakeholders, back to the community residents, back to the people that your research should be serving. So if you go through it, you'll see we have outcomes, we have objectives, key actions, all that stuff. Look at the key actions. There are things that people in this room can do to work with territorial departments in support of actions outlined in that document. We do have a longer-term vision. Many of our regional Indigenous governments are in the process of articulating their own research agendas. Some of them have pretty well established research agendas. Gwitchin, for example, have had one for about 6 years. We're doing what we can in the short term to establish priorities within the government, but our longer-term vision is to create an agenda that's reflective of the needs of all levels of government in the territory. And I hope it doesn't ruin next summer. It probably will, though. We're attempting to make progress in the short term, but it'll probably be more like a 3 or 5 year sort of process. So that's it. I'm a little over 10 minutes. Thanks.
Okay, thank you, Andrew. So a lot of good ideas there and how to interact with the government and things, and look forward to seeing the action plan. So our next speaker is Samantha Jones, Sam, and she is a graduate student here in the Department of Geography. So come on up.
Oh, that's okay. Yeah, and I can advance with the arrows on here, right?
Yeah, and there is a laser there.
Perfect. I shouldn't need it, I don't think.
There you go.
Perfect. Great.
Okay.
Thank you so much. Thank you for inviting me to speak today. I'm going to talk a little bit about the carbon cycle today. So I'm going back to some of the hard science topics, but I think it ties in nicely with a couple of the talks we just heard. I was really excited to hear some of the themes that people have discussed this morning. And I'm going to talk to you about the inorganic carbon cycle, so carbon dioxide, and I'm really interested in looking at that nice transition zone. We've heard about shorelines a little bit between the sea and the land, and understanding the coastal ocean carbon cycle, which is important for things like ocean acidification, which you've also heard mentioned this morning, by looking at a whole continuum of the watershed on land, so lakes and rivers, that are then connected with the coastal ocean. So in case you're not familiar with carbon cycling, I'm going to start with a quick crash course on carbonate chemistry. So we've heard a lot about carbon dioxide in the atmosphere, but carbon dioxide is also found dissolved in natural waters, so lakes, rivers, ponds, even reservoirs, and also ocean water. And when CO2 dissolves in the water, it forms carbonic acid, which is a weak acid, and that's by reacting with the water molecule. And so that's what is going on when you hear talk about ocean acidification. That acid then breaks up into other ions, and when you hear me talk about dissolved inorganic carbon today, I'm talking about all of those things together. So the dissolved carbon dioxide, the carbonic acid, and the ions that breaks up into. So just a little bit of terminology defined for you before we move into the rest of the talk. My entire project looks at all of the connection between a lake, river, and coastal ocean system, and I'm interested in how does the inorganic, so that carbon dioxide cycling work, and where is the carbon coming from, what are the sources, and what are the fluxes? So how does it move between the different environments? And that's both between different bodies of water, but also between the atmosphere and the water. And in this talk today, I really want to focus on ice, in particular ice on land, and how ice in the lake and the river influences what's happening in the coastal ocean. So looking at the systems connected rather than in isolation. I work in Cambridge Bay, which is in Nunavut, which is marked by the yellow star there on Victoria Island. And the map here to the right shows the different areas that I work in, so connected lake, river, coastal ocean system. The lake is called Greiner Lake, and you can see part of the watershed outlined with the bold red line, but it's a lot more extensive than the area of this map. Freshwater Creek, which is just a couple of kilometers long, and that discharges both water and dissolved materials into the coastal ocean in Cambridge Bay. All of the colorful dots you see on the map represent our data collection stations. So we have sensor data, we have things like temperature, dissolved oxygen, salinity, different parameters from sensors we lower into the water column, and at selected stations we also collect water samples. And we try to do time series sampling. So that is, we go out to the sites and we collect samples at a repeated interval over several years. In my case, I've been up here 3 summers in a row, a total of 80 days of fieldwork, and so I have a time series from 2017 until this summer, and I'm going to show you some of that today. Before I continue, I'd like to talk a little bit about breakup. So that's one of the themes of my talk, and when I talk about breakup, I'm talking about the spring melt season, and it's a really dynamic time. We have our own spring melt here, right? The days get longer, we start to see the snow and the ice on land melting, and melt ponds are also forming on the sea ice at the same time. We establish the seasonal streams and rivers that may have been disconnected or low flow during the winter, and then the land and sea become connected again. So we've, in my field area, connected up the watersheds with the coastal ocean because that freshwater creek doesn't flow in the winter. It's completely frozen. And then after that's happened, all of the sea ice melts. So you actually have kind of 2 melt things happening. You have melt on land, and then you have melt in the sea as well. On the left, I've shown a seasonal wheel from the Nunavut Planning Commission, and this is from the 2016 draft land use plan, and it shows the 6 Arctic seasons. So they divide up the year into 6 seasons rather than 4, and I'm really interested in the transition between fully frozen to fully melted and what's happening in between. So now I'm going to show you what this year looked like at the river. This is a series of photos of Freshwater Creek. You're looking north towards the watershed, and I'm standing on a bridge a lot of the times. I'm trying to look in the same place. You can see the hill kind of repeated in a bunch of the images, and then you see in and around the bridge as well. On the top left, at the end of May, beginning of June, everything is still fully frozen. That river is not flowing. It's completely ice and snow. And then at the beginning of June, we start to get surface melt, ponding in and around natural depressions. And finally, we have enough meltwater to create a discrete channel that's then taking that meltwater and moving it out to the ocean. After a while, the melt progresses enough that the lake can open up. And so that lake has been dammed up by ice until enough melts happened that now that opens and the lake can become connected with the river. And this is the point at which we're actually connecting the watershed to the coastal ocean. At first, the river's just draining the snowmelt, and then all of a sudden, you've got the lake water coming in. And once that happens, you can see on the bottom there, it's unstoppable. The amount of energy with that liquid water melts everything within about a week and a half. And this was cool because you'll notice that there's a photo of June 18th in the morning, and June 18th in the evening, and that breakup of the lake actually happened in the middle of that day. So you can see a dramatic change in the water level. Now I want to talk a little bit more about the lake. So in the lake, we have lake ice, but it's not frozen to the bottom, and that river's completely cut off during the winter. But stuff is still going on in the lake, and under the ice, we're slowly depleting the oxygen and accumulating carbon dioxide. The ice presents a physical barrier, so that prevents that from emitting to the atmosphere, and it also can't discharge to the sea because we don't have the river. So under the lake ice, we see a progressive decline of the amount of oxygen dissolved in the water column and accumulation of greenhouse gases, including both carbon dioxide and also methane. And you can see on this plot a couple of different profiles. So the y-axis is depth, so surface of the lake at the top, going down to the bottom, which is about 8 meters at this station. And then on the x-axis is oxygen. So starting at the purple and the orange line, that's in the summer, well-oxygenated, well-mixed water. And then over the winter and into the spring, we progressively decrease the amount of oxygen there. In some places to hypoxic, which is under about 30% oxygen, or anoxic conditions, which is really harsh environment to live in. Now, the cool thing about my field work, and I think my field team would disagree, is that we do these things called 24-hour sampling campaigns. And they're modeled after a paper that came out of Scotland, where they go out every 4 to 5 hours, take water samples, and check out what's going on in the river. And they're looking for daily cycles that show that a river is an active place of carbon cycling. It's not just a passive conduit. And so I wanted to replicate that. And this year when we went out and did that, we were lucky that the lake actually opened up in the middle of our cycle. And so we extended it because everyone was so thrilled that we caught this. And we were able to catch the before and after chemistry of the river, which shows the difference between the snow melt in that initial channel to the opening up of the lake, which then connects up with the ocean. And that's what you see here. So the blue line is showing you conductivity, and conductivity is really a measure of how much material is dissolved in the water. And so relatively pure water, like snowmelt, is going to have a low conductivity, and that's what you see on the lower left part there. Once the lake opens up, all of a sudden we're getting water with more stuff dissolved in it from under the lake ice, and it's moving into the stream. So we can see a distinct difference in the water that's there. And we also see a change in the oxygen. So that low oxygen water that's been accumulating in the lake, the high CO2 water over the winter, is now moving into the river. But it doesn't stop there. It also continues to move out into the coastal ocean underneath the sea ice, which is still present at this time, and we can detect it in the marine environment. So this plot shows our river station up on the top right there, where we measure close to the mouth of the river. And then as you move out into the bay, that pin in the middle, B1, is one of our flagship stations, and it shows you the location of where the next 2 plots are going to come from. And we can see this high carbon dioxide water that's in the river moving out under the sea ice, and it creates a peak out in the bay under the ice. And so that's really interesting for a couple of reasons. One of the things I like to point out here is that that peak is relatively small once it gets out and spreads out around the bay, and it's short-lived. So this is a really transient phenomenon. And if we're not there doing the time series sampling, it would be easy to miss this. The other thing that you can see is a low peak in the carbon under the ice in the surface water in the bay, which is on the top plot, and that's when all the sea ice melts. And so then you're getting this big influx of relatively fresh water that dilutes the carbon in the upper part of the water. So you can see these kind of 2 different events, one from the melt on land and then one from the melt at sea. So I'm going to leave it there, but I just want to convey a couple of key points. I hope I've showed you that ice plays an important role. And that breakup is really a fast-paced, dynamic change. And if you're not out there doing high-resolution sampling, it could be easy to miss this type of information that's really important for carbon cycling, for carbon models, and understanding the baseline conditions. And using this sort of continuum approach is really helpful at getting insights that you may not have gotten if you're just looking at one of these environments in isolation from the other. So if you'd like to hear more about that, you can grab me in a coffee break or at lunch, and thank you. Enjoy the rest of the day.
Thanks, Sam. So, and our next speaker is approaching the podium now, is Dr. Brian Moorman, who's a professor in the geography department and also an ENA board member, I might add. And so, because this was the ENA Board of Directors idea, I think it was Brian's actually. So we're pleased to have him here with us, so. Yeah.
Thank you so much, Melanie. And I want to thank the previous speakers, Mary Beth, Ravi, everybody who led up to this, because you provided a really nice framework and background so I don't have to cover it in mine. We know that there's lots going on in the Arctic, and we know that it's important and fantastic. And I don't know who came up with the title for today, for Arctic on the Edge, but I like to run with it because I'm studying the edge in the work I do, looking at the coast. And so my title is Destruction of the Edge, because I'm looking at coastal erosion. And it's not just me. I just want to acknowledge that I've got co-authors in this, Andrew Clark, my PhD student, Dustin Whalen from the Geological Survey, as well as a whole bunch of other people that have been working with us over the last, well, several decades. It's actually a long-term project. So it's important to study the coastline. Thank you, Ravi, for that the introduction and showing how modeling the coastline is important. But using southern modeling techniques in studying northern coastlines can be complicated because permafrost is there, there's massive ice, retrogressive thaw slumps mean that the coastline is behaving in a different way than when you have unfrozen ground. The picture on the bottom left, you can see these retrogressive thaw slumps working their way back from the coastline, and I drew a cute little boat in there for scale. These are big, big features. That's kilometers long coastline that's being eaten away. And so mapping just the coastline doesn't tell you the whole story, and that's what I wanted to do here with this project, is tell more of the story, get into the complexities of the processes behind what's going on. So we can map just the coastline, but it doesn't tell you what volume is going into the ocean. And we're talking about the volume of sediment that's polluting the ocean, the volume of carbon that's coming out of the permafrost going into the ocean and the atmosphere. There's a disclaimer or telling you the story at the end already. The key, though, is that all the volume is not sediment. It's not all carbon. A lot of it is water, and that's why it behaves the way it does. So I got that little picture on the right showing a chunk of the permafrost that we cored out of the ground, and the dark bits are actually pure ice. And so when we thawed that piece of core, all that you have left is a little puddle of water in your hands. So the objectives for this project were to look at the evolution of the coastal zone over a long period of time. I was lucky to have worked in the same area for, well, a long time, 30 years. Determine the relationship between the permafrost and the coastal environment and the effect on coastal retreat. And the overall goal for the long term, hopefully, is to develop an integrated process model so that we can further contribute to the analytical and computational models that Ravi was talking about earlier. So let's see how far we did. I don't need to talk about the significance. One of the places that I study is right near the town of Tuktoyaktuk, where they're actively moving the houses away from the coast inland because the coast is eating into the town. And not only is there a local significant impact, but we're talking about huge amounts of sediment and carbon that are going into the ocean and changing the global climate system as a whole. So to put us into perspective where we are, we're talking about the Mackenzie Delta, the satellite image. You can see all the thaw lakes indicating that there's lots of ice in the ground, or at least there was. The town of Tuktoyaktuk is yellow, and Peninsula Point, where we're studying, is just to the southwest of there. The sensitivity map that you see on the left indicates that while there's lots of places across the Arctic where the coastline is sensitive to climate change, the Mackenzie Delta area is one of the most sensitive. So specifically, the site we're studying is called Peninsula Point, and it was one of the very first places I went to in the Arctic when I was an undergrad student, and one of the reasons why I fell in love with permafrost, because this permafrost was falling apart and there was nothing permanent about it at all. From satellite imagery, same way that Ravi showed with his work, we've mapped at the coastline at the at the site has been retreating since the earliest satellite and air photos that we have back in 1972. And from visiting the place, we see that there's lots of ice in the ground, like thick 15-meter bodies of pure ice. So when it gets exposed, it literally turns to a liquid and flows into the ocean. So it's a complex place to work. So how do we work there? Well, the way we worked has changed over the years. When we first started going there, we were dependent on satellite imagery and air photos, very few air photos. We were mapping the area with theodolites, and we were coring into the ice to see what the subsurface looked like. And I was lucky enough to be able to use this very first, very slow, labor-intensive ground-penetrating radar system so we could image underneath the earth. Nowadays, we've got drones that we can fly around with cameras to get super high-resolution images. We have structure for motion software that turns those into digital elevation models so we can actually figure out the volumes that we're talking about. We have real-time kinematic GPS to have precise surveying of the landscape and to ground truth, all the stuff we have. And we have new GPRs that we can drive around behind a snow machine and collect thousands or millions more data points than we used to in the past, so that we can actually map what's in the subsurface as well as what's on the surface. So, what have we found? Well, the first, here's a little bit of data, actually results that we found. The first thing we did was compare the topographic maps from the first one we had from 1986 that was done with one of these theodolites. And you can see the topographic map that was created in the the top left there, converted it to a DEM, compared it to one of the most recent ones, and a couple of interesting things. While the coastline retreated by about 60 meters between 1986 and 2016, the headwall retreated by over 170 meters in some places. So you're seeing that there's a huge volume of material that was dumped into the ocean, even though the coastline didn't look like it moved by that much. So we're looking at a couple million cubic meters of material that was on land is now in the ocean, even though the coastline didn't look like it changed so much. When we look at those profiles in detail, we see the standard thing that we would expect to see. So if these are just a bunch of cross profiles through our study area from on land on the right out to the ocean on the left, and P1 on the top left there, you see the head wall retreat. So the coastlines move back a little, but the head walls move back a lot. Okay, that made sense. The one on the bottom left shows that some places the head wall moved back, but the sediment that was coming off that head wall was actually being deposited on land before it made it to the ocean, so that it was preserving the ice that was underneath it and protecting the ground so that it would be stabilized, at least for the short period. One of the really surprising things we found was in the profile on the bottom right, way back from the head wall, in the terrain that we thought was stable and not moving, we actually see that it's subsiding as well. So we're not seeing complete destruction of the land like you see in these retrogressive thaw slumps, but we're losing volume there as well. The permafrost is thawing, the ground ice is melting out and just slowly leaving. So if we take this data and model what its contribution to the ocean is as far as sediment goes, we can use 3 different models, and this is where the complexity comes in. If we just use a simple coastal retreat model, if we just say, here was the coastline then, here's the coastline now, the bluffs are this high, how much volume have we lost? Calculation, about 720,000 cubic meters in our little short stretch of coastline. Okay, that's cool. That gives us an idea how much sediment's being dumped in the ocean. But if we then take into account that the head wall is actually retreating much farther than the coastline is, it becomes more like 2 million cubic meters. Oh my goodness, this is a dramatic difference. But because we're also looking at the subsurface with the radar and taking cores, the picture on the right shows that a lot of the subsurface is just water. So actually, we're not dumping 2 million cubic meters of sediment into the ocean. We're really, if you take that water out of the massive ice out of the model, you're dumping in just a little over 800,000 cubic meters into the ocean. So the moral of the story is you're seeing dramatically different numbers. If you don't know what the actual process is and what the ingredients, what's in the subsurface, you're kind of hooped. So that was the first discovery. That's kind of cool. We need to investigate that further. The other thing, when we were surveying the subsurface that we discovered, was that the GPR worked really great. It was awesome. We could map out, with the drones or the survey instruments, we could map out the surface, and then the GPR would allow us to see where the top of the ice was in the subsurface. And it was more complex than we thought because of this deposition of sediment. But also the bottom of the ice was more complex than we thought. It was undulating, and it's not easy to extrapolate is one of the lessons we learned. But the real surprising thing was the bottom of the ice was below sea level. So if the bottom of the ice is below sea level, what happens when you go out into the ocean? Is there still ice there? And sure enough, that's what we found, is that when we did our radar surveys out into the ocean, and here's one that goes across the bottom there, we went from land on the left out into the ocean on the right. And for the first couple hundred meters, you don't even see the bottom because it's so shallow. And then you can see that undulating layer where it's labeled at thermokarst zone. Ice is starting to melt out in the sub-bottom out 200, 300, 400 meters from the edge. That means ice is there. So that means it's been preserved way out into underneath the coastline, in the water for a long period of time in the shallow water zone. And that's because the thermodynamics of it all allow it to be preserved. So there's a lot more I could go into on this, but I want to wrap it up so we can get to coffee. So the result is that we're now developing a linked onshore, offshore, process-based model so we can better understand what's going on as far as sediment contributions to the ocean and CO2, carbon contributions to the ocean. And we need to take into account things like the ice content of the permafrost onshore, because it makes dramatic change or difference as to how the shore is going to react to coastal erosion. How thick the sediment cover is. Is it all going to wash away, or is the sediment going to redeposit and preserve the ice for later times? What the surface energy balance is, and how the sediment is being redistributed once it starts eroding. But this is all completely reliant on what's happening offshore at the same time. You can't look at that alone, just like you can't look at the coastline alone. On the offshore, you got to look at wave action. That's one of the things we're seeing dramatic changes in the Arctic Ocean, is this height and intensity of the waves and how frequent the storms are. That controls how fast the sediment is being evacuated from the nearshore environment. The bathymetry, whether you've got this shallow shelf coming out from the coastline or whether it dips off really quickly. And that determines where the sediment goes, but it also determines what the thermodynamics are going to be underneath the ice. And then finally, water temperature and where the sediment is going will control what the result is of all this activity. So that's where we are now. Hopefully, another 30 years from now, we'll have a better handle on what's going on in the nearshore. Thank you.
But our next speaker is Dr. Brent Else, and he is a professor in the Department of Geography, and is going to talk about Arctic communities and things. So let's give him a warm welcome.
Awesome. Thanks. So before I get started here, I just want to acknowledge the students and technicians that have contributed to some of the research results that I'm going to show today. I'm going to show a few research results, but really my talk is about how we do climate science in the Arctic. And Maribeth already introduced a little bit about the Mosaic Project, and I just wanted to, I'm not going to speak too much about it, John's going to speak about it. I just wanted to mention it because the Mosaic Project is one way to do climate science in the Arctic. And it's really important. It's really important that we revisit these deep Arctic basins regularly to see the kind of climate change that Maribeth was talking about. And it's also really important because one of the big driving forces behind doing a project like Mosaic is to try and understand what goes on during an entire year in the Arctic, which is something that that we physical scientists don't always do super well. Like, we've heard about this a couple of times, like research projects that come in and come out really quickly. And so there's some fairly important processes that happen through the Arctic winter and through spring that we don't understand super well. The only drawback to a project like Mosaic is that it's super tough to organize and it costs a lot. Like a Mosaic costs something like $200 million to operate, right? And I mean, when you think about it, really what that money is going into is it's going into creating a platform, the polar stern, and then supporting that platform with other icebreakers and stuff so that scientists can do this research over the course of an entire year. But there is another way to do that, and that is to try to find ways to partner with Inuit communities where there are already people there all the time, all year round, right, as opposed to like putting a ship there for 1 year. So this is a map of all the Inuit communities in the Canadian Arctic. And what I want to do is I want to talk a little bit about how my research group has been doing climate research in Cambridge Bay, which is right about there. So here's some pictures of Cambridge Bay. Cambridge Bay, here's a picture from the sky. Cambridge Bay has about 1,500 people. I think most of them fill out their census forms. I haven't heard of this like 100 versus 700. That's pretty amazing, actually. So there's lots of people there. Cambridge Bay is a nice place to do Arctic research as well because there's some logistical support for research there in the form of the Canadian High Arctic Research Station, and there's some other bits of logistic support as well, like there's a research vessel there, the Martin Bergman. So it's naturally a good place to do research. But what we've been trying to do is trying to find a way that we can do this year-round kind of research out of Cambridge Bay, and we've been doing that for a few years. So I'm going to show you just a few examples of the kind of research that we're doing there. A couple examples. It's going to be really quick because I don't want to get too deep into the science here, but one of the things that we're doing revolves around this really high-tech weather station that we built on a small island about 30 kilometers from Cambridge Bay. And what this weather station does is it actually measures how CO2 moves between the ocean and the atmosphere. And in the Arctic, there's this big question about what role sea ice plays in that exchange. It's not super well known. And one of the reasons why it's not super well known is because it's tough to make these measurements through the entire annual sea ice cycle. So what we've been able to do is we've been able to work with people in the community, work with the Hunters and Trappers organization, work with local people that we've hired out of the Nunavut Arctic College's environmental technology program. And those people have been able to help us keep this tower running for most of the year. We always have some problems with power outages and stuff like that. And they're able to get there by boat during the summer when the ice is gone, by snowmobile in the winter, or even by helicopter. We have some support from PCSP at certain times of the year as well. And what we've been able to do, I've got an example here. This graph shows basically an annual time cycle of this CO2 exchange. So it starts from early May when there's full ice cover, goes right through ice breakup to open water, and then descending into winter and ice freeze up here, and then right through to the end of December where you've got back to your full ice cover. And basically what it shows is this really amazing dynamic pattern where the ocean breathes in CO2 here during the breakup and then sort of breathes it out during the open water season and then breathes it back in during the winter. And this is not something that anybody else has really measured with this kind of resolution anywhere else in the Arctic. And we're using that to try to understand what the key processes are that drive this. And this is really important because this really helps us understand basically how much CO2 is accumulating in the atmosphere, or like what role the oceans play, the Arctic oceans play in that accumulation of CO2 in the atmosphere. And also, as Maribeth mentioned and as Sam mentioned, this CO2 exchange is important to understanding ocean acidification and stuff like that too. So that's one example of how we're able to get really interesting time series. Here's another example, which is kind of building on the presentation that Sam gave. So we've also been working with local people, training local people and learning from local people to collect samples, to collect water samples throughout the year close to Cambridge Bay. And here it's really important that we have that partnership with local people because you can see like some of these conditions that we're sampling in here are pretty difficult. And like Andrew said earlier, it's really important that you work with local people so that they can help you solve some of these problems. Like for example, who would have thought that it would be a good idea to use a sea-doo to do water sampling in the summer? Not me. I still don't think it's such a great idea, but it makes for a cool picture. But anyways, again, what we're able to get is these really awesome time series. So this time series is looking at dissolved methane. Sam was talking about dissolved inorganic carbon, but this is dissolved methane. And again, we've got these time series where we start from like the ice cover season, go through that breakup season that Sam was talking about, and then into the open water. And what we see is when that river starts to flow, like Sam was talking about, we get this big pulse of dissolved methane from the river. That's in the red there, and then it advects out underneath the sea ice. So if you think back to that picture that Maribeth showed where somebody had like drilled a hole in the ice and then lit the methane on fire, if you don't do that, some of the methane is going to go through the river and end up underneath the sea ice. And we don't exactly know what happens once it gets under the sea ice, but those sorts of things are really important to try to figure out, because if that becomes some sort of a sink, like that methane gets consumed, then that might be important in understanding climate dynamics in the Arctic. So those are kind of the kind of things that we're doing. But I wanted to emphasize as well, so Maribeth and Andrew brought this up too, we need to be really careful that when we are working in these Arctic communities as a platform for climate science, that we're trying to find ways to work with them. So the ITK has produced this National Inuit Strategy on Research, which is a really good guiding document to try to inform this. And they're very clear there that we need to be careful that we're not just going in there and extracting those interesting scientific results like, oh, this CO2 flux is really cool, or oh, this dissolved methane is really cool, and we just pull that out and get out of there. And that's what this opening letter, which always, whenever I read this, it really strikes me that this is a really important thing to be trying to do. So lightning talk, so I don't have a ton of time to talk about all the ways that we're doing this, but I have one example of how we try to do this. And it's in the form of a video that we just made. So this is always the moment of truth here. Hang on a second. Yep. Is that showing up? No. Okay. Yeah. Nope. Got to get it on the other screen. Did it. Okay, here we go. My name is Brent Else. I'm an associate professor at the University of Calgary in the Department of Geography. One of the things that we've been doing over the past few years is setting up small weather stations that the community can use to find weather conditions in important areas around Cambridge Bay. We received lots of feedback from the HTO and from other people that weather conditions can be very variable between sites. So even if you look at the weather here in Cambridge Bay, the weather out at 30 Mile might be very different. So the idea is that if you're traveling there, you can look at that weather and see what the weather conditions are at that site. This weather station is measuring wind speed, temperature, relative humidity, and pressure. So if you want to know what direction the wind is blowing from, how strong, what the temperature is like out here, you can check that on the internet. The main people that are involved in this project are myself, my research group, and the HTO, who have been suggesting the sites where we set this up. The HTO has also sent guides with us to set up some of these sites. And then we have also involved students from the Nunavut Arctic College. And it's really important that we have guides and students involved because we're not here year-round. Sean and Francis rode here a couple weeks ago. One of the pumps in this box had stopped working, and they managed to get it going again, and they actually changed things a little bit, so we're getting a better flow rate than we were before. We're hoping to add more weather stations in the future and also train people in the community that have the skills to collect this type of data and to use these types of instruments. Cool. Okay. Let's see if I can get back to where I was here. Maybe not. I'll let Melanie solve this maybe. Oh no, I got it. Good. Okay, so it's a little bit frozen over here. That's okay. I'm done, really. Lightning talk. No conclusions. It's all done. But anyways, we're doing this in other ways too, and I'm really happy to talk about that if anybody is interested during one of the breaks. And I will end it there and try to fix the problem that I just caused over here. Thanks.
Okay, thank you, Brent. And next up, we've got Dr. Rob Hubert, who's a professor in the Department of Political Science and is also a research fellow, thank you, at the Center for Military and Strategic Studies and there's another S in there. So, so please welcome Dr. Rob Hubert.
Well, as I like to say, now for something a little bit different. It's always fascinating to come to these talks and just to hear what our colleagues are doing in terms of examining on the Arctic. You'll see that even for the title of the conference here, I had a little bit of fun relating to what I'm talking about. You'll notice I said Arctic on edge, not Arctic on the edge. Because really what I'm here to talk to you about in the 10 minutes that I have available is the focus of my research, which of course is talking about one of the major transformational elements of the Arctic, and that is of course the geopolitical context. Now, to cut to the chase, part of what I'll be talking about is that there's a lot of discussion in today's media that we are returning to a Cold War. My contention will be, of course, that the Cold War never ended. We took a bit of a break, caught our breaths, but the underlining features of the Cold War during the Cold War period are simply and very unfortunately being reinvigorated to a degree where we are entering into a very dangerous international system. To a very large degree, we are returning to the great game. And what's driving the great game is the fact that from a geographical perspective, the three great powers of the international system, United States, Russia, and increasingly China, from a geographical position, it is the Arctic that is the interface between all three of them. What makes it particularly problematic are developments in new weapon technologies. Most people are not aware that during the Cold War, the Arctic was actually the most dangerous zone of the entire international system because it was out of sight and because the weapon systems that we were talking about, submarines, long-range bombers, were basically based out of sight. Most people did not realize that if a nuclear exchange actually was to develop between the NATO countries and the Warsaw Pact, the major ground zero was going to, of course, be over the Arctic. And if that nuclear war was to be deterred, it was actually deterred by actions that both the Soviets and the Americans took vis-a-vis the Arctic. So once again, we think sort of the Western Front, we think Germany, but the reality is the Arctic was the critical location. We thought that this had ended at the end of the Cold War when the Soviet Union imploded. And we thought that the geopoliticals had sort of created the Arctic as this exceptional location of peace and cooperation. We now have to appreciate that when we talk about the Arctic, notice how the theme of all the scientific discussions are, of course, that you cannot talk about the Arctic outside of the greater physical environment. In other words, all the discussions that we've heard so far have made it very clear you can't think of the Arctic in isolations. Well, when it comes to the geopolitics today, you cannot think of the Arctic in isolation. We have to recognize that we are entering into probably one of the most dangerous eras that we have faced since the end of the Second World War. What we see is a direct challenge to what can be described as the transatlantic hegemonic era, the period in time in which Western liberal democracies were able to come together and basically have an agreement of a common cause in terms of their ideology, a commitment to liberal democratic practices, as well as a commitment to open economic transactions. And we were able to resist a series of challenges to those ideals and interests. Through what we call hybrid warfare and other aspects, we now see, and you can just pick up the paper to see what's happening in the United States, see what's happening in Great Britain, that under the auspices of what we refer to as hybrid warfare, we now have very strong suspicion that the encouragement, be it Oxford Analytical or any of these other means by which that core of consensus is now being undermined in each and every one of the Western democratic countries. Now, what does that have to do with the Arctic? Well, the Russians tell us in 2007 that they are going to be a great power and they're not going to accept us. In 2002, China has a defense budget that's less than us being Canada, and they have now moved into having the second largest defense budget because they have made the decision as early as the Tiananmen Square incident to also challenge the West. So where does it take us into the Arctic? Well, when we consider the Russian return to great power status, we have to ask the question, how did they do it? Well, the first thing you do if you're a great power is you rebuild your nuclear deterrent. Canada, Norway, United States, and United Kingdom had spent billions of dollars helping the Russians actually get rid of their nuclear deterrent, or much of it, during the period of the 1990s through a program of AMEC and the G8. The Russians, when they decided in 2007 that they would be a great power again, have been reinvesting heavily in the development of their nuclear deterrent, which has to be placed because of geography in the Arctic region. As they redeveloped their nuclear deterrent, they then needed to rebuild the offensive forces to protect it. So they have reopened and rebuilt new aerospace bases all along the Northern Sea route that are nominally to protect shipping along the Northern Sea route, Northeast Passage, but are really there to protect their nuclear deterrent. But also, starting in 2014, they've also discovered that these forces are very good for power projection. So when they have decided to move into the Ukraine, when they have decided to challenge the Baltic states, they are doing so from the northern bases where they are a hegemon. So as they've returned to great power status, they have rebuilt. They have had as one of their core security policies to prevent further expansion of NATO to their doorstep since 2008. Since that time period, NATO has not admitted a single country that shares a border with Russia. We have admitted 3 countries from the former Yugoslavian, but we have not admitted countries such as the Ukraine or any of the other countries that share a border with Russia. So in this context, the Russian power projection from the Arctic has actually been successful. We don't like to acknowledge that in Canada, but it has been. So we also see, of course, the issue that the Baltic countries are threatened. Canada has forces there as deterrents. Finland and Sweden were looking towards membership, and it's an open question in terms of how you do it. They are de facto members. In other words, if you talk to NATO officials, they will admit that for all intensive purposes, under the Partnership for Peace, they have now become NATO members, but because of this fear of what the Russians would do in response, because every time a country on their border has sought NATO membership, Russia has used military force to stop it. Think Georgia and Ukraine. And so in the north, we now have the Finns and Swedes who increasingly want to be in NATO, but know that they cannot. Now, where does the United States fit into this? Well, we of course have the United States that can't make up its mind that it's an Arctic country. Though in very recent months, we have seen the Americans increasingly acknowledge the return of the geopolitical realities. But the Americans have also been doing some very strange actions. They have, of course, had that very bizarre incident where Trump talks about buying Greenland, and when everybody laughs at that suggestion, actually gets so pissed off that he cancels the meeting with the Prime Minister of Denmark that he was supposed to have in September. The Americans have been, for bizarre reasons, talking about challenging Canada on the Northwest Passage, even though if they succeed, that then means that Chinese and Russian submarines have the international right to sail through the Northwest Passage submerged. And so, once again, this American leadership seems to be acknowledging. But more to the point, the Americans, and once again this has not made the media, have revamped their nuclear policy. They have introduced new doctrine that says that they are going back to the concepts of engaging in limited nuclear war. This fundamentally challenges the Russian nuclear deterrent and creates a dynamic that is going to be increasingly dangerous. And just so you know, the Americans have actually started building the new tactical weapons. They have low-yield missiles that they are now putting on board their traditional boomers, and they also are developing a hypersonic delivery system for a limited nuclear warhead. So in other words, the Americans are changing the name of the game that is then going to affect how the Russians. So we get this dynamic that is continuing on this aspect. The other side of the coin is that the Americans are also committed to anti-ballistic missile defense. And if you are going to defend the United States, you need to defend it from Alaska. So Alaska, and Fort Greely in particular, has become one of the most important points of defense for the Americans from any Asian attack. On the other side of the continent, Thule, and this is where the bizarre aspect of Greenland come in, Thule needs and is in the process of being modernized. And so once again, you see the fact that the Americans, even if they want to ignore the Arctic, still cannot do so. Now China. China's a new entry. Of course, everybody was, when the Chinese showed up on Canadian Arctic territory in 1999, you'll recall that the Zulong, the snow dragon, showed up at Tuktoyaktuk. Now, most people thought, well, what are they doing there? They won't be back. They have substantially invested in science, economics, and governance issues. Starting in 2014, the Chinese begin to practice how to send their navy into Arctic regions. They've been into the Bering Sea. They have visited almost all the European Arctic states, except for Norway. They are still angry at the Norwegians for granting a Nobel Peace Prize to the dissident, and they have refused to go to Norway as a very clear political indication. They've been operating with the Russian Northern Fleet, doing live sails exercises. They've also been in the Canadian water. In 2017, the Snow Dragon sailed through the Northwest Passage. Once again, they followed Canadian rules, but it's becoming increasingly evident that where the Snow Dragon is sailing is also a lot of locations where you would send a submarine. And the suspicions are what the Chinese are now doing is preparing for the development of an ice-capable either SSN or SSGN as they continue their economic and naval modernization. So where does this take us? For the United States, their security is entirely tied to the Arctic. But as they develop their security in the Arctic, the Russians respond. The Russian security, national security, is the Arctic. So it's not about fighting over a continental shelf. It's not about race for resources or any of the thing that gets into the media. We are talking fundamental defense requirements of the two most powerful nations that now oppose each other. And if you really want to get scared, think about the possibility that the Russians have successfully infiltrated the highest levels of the American governance system. If you look at Trump's actions with the Ukrainian president, if that was planted under hybrid warfare, this could not be a more striking example of destroying the NATO alliance than having someone do something like that. And so you then come back to the Arctic. The Arctic is where the two most powerful states have their security interests tied. Now, to get to the third part of what I call the strategic, the nasty environment, the trilateral aspect. China's defense budget is now at $300 billion. They are the second largest defense budget. They are going to be in the Arctic. They are going to be, right now, they're friends with the Russians, but we know that that will not last for much longer. And so we are coming into a security geopolitical environment in which the Arctic becomes the critically most important location, where we don't know where the Americans are going. We see the Russians pushing on this context, and the issue is, when will the Chinese show up in force in the Arctic? Thank you very much.
Thank you, Dr. Huebert. A lot of food for thought there on how we, how things will transpire as we get into the next election cycle and things. So, so we're going to switch gears here. We've got Dr. Marc Poulin here, who is a, let me get my notes here to get it right, professor in the Faculty of Medicine and Kinesiology, and he's going to talk about some brain research, neurotechnologies in the north and things. So come on up.
Thank you very much, Melanie. So sorry for the pun, but that was a pretty nasty talk. That's why we need someone like Rob on our team, and you'll see what that means coming up. Okay, so it's a pleasure for me to share with you some news of our new training program that we were awarded from NSERC earlier this year. It's a 6-year training program, very multidisciplinary. And we have the Arctic Institute of North America as one of our partners. And I'd like to share with you some of the details of the training program and the opportunities that lie ahead for the next 6 years. So NSERC contributed 1.7 million, but the total budget, including the in-kind, is a $6 million training program. So what is neurotechnology? This is about drugs or devices or methods to enhance function and monitoring of the brain and the integration of various physiological systems in the body. So this builds on a huge investment at U of C in the area of $100 million over the years. And as I said, with the cash and in-kind budget, it's over $6 million contribution dedicated to trainee salaries and provides advanced training in key brain neurotechnologies and professional skills, including innovation and commercialization. And we are very keen to pursue this with our partners, including ANA, and providing training opportunities for trainees from the far north. So this program aligns with an interesting number of strategies at the university that focus on innovation and commercialization. Here, so if I just go around, whoops. So the Hotchkiss, this program is based at the Hotchkiss Brain Institute. They've hired a new director of innovation and commercialization. Calgary Innovates is an entity at the university here to help with commercialization and development of intellectual property. We are working closely with Campus Alberta Neuroscience, which is a government agency now working through the Ministry of Economic Development. The Hunter Hub is really a new hub for entrepreneurship at the university. NeuroNexus here, a program to help trainees develop new ideas and turn their ideas into commercialization. And of course, Brain Create is part of that, and we are also bringing ANA on board to work with us on this. So what will Create create? It shows you here on the right-hand side a number of things that the program will create. So it's a personalized education at the master's, PhD, postdoctoral level. There's high mobility, enhanced mentorship, and extreme physiology as a test bed for innovation. So it's really highly interdisciplinary. So you can see here it's focused on innovation, education, and commerce. And these are different hubs, if you want, or themes within the program. It's really looking at environmental, geographical, and biological extremes. So the objectives of the program is to really increase neurotechnologies and to study, monitor, and manipulate brain functions, to promote societal, scientific, and economic advances, and to improve the quality of life. So what we want to do is to increase the number of highly qualified personnel with essential knowledge required to work in new neurotechnology industries, increase the number of HQP who can lead innovation and commercialization, increase the number of HQP focused on innovation and commercialization of new technologies designed to address safety and health issues in Canada's remote communities, and provide accelerator opportunities in neuroscience for both research and education to underrepresented natural sciences and engineering trainees. So over the course of the next 6 years, we're proposing to bring on board over 100 trainees. This is the distribution of the trainees. We have a number of undergraduate summer studentship opportunities that will be available. These are the years that you can see on top. A number of master students, shows you the new intake here in parentheses, PhD students, postdoctoral fellows, and the total here over 6 years. And so Brain Create, the program, has a commitment to trainees from Northern Canada. There's dedicated places for trainees from the North as part of this program. So we're very excited about that. Schematically, this is what this looks like. You can see here the academic component in blue, the research component in red, and the training component in yellow. At the moment, the program is based in the Department of Neuroscience. We're exploring whether or not this will be a multi-program approach in the future, but for the first year, it's in the Department of Neuroscience. And we have a number of institute partners on board, as well as other partners like ANA. And really what we're looking at is to really provide a personalized and new way of education for the next generation of trainees. This shows you a roadmap of what a typical PhD program would look like. We're going to recruit and select the best students for this program. They will have a boot camp. There's a number of core courses, core elements, elective elements. Some of them are on-site and off-site. We have some extreme expeditions that will be part of the electives. At the moment, these expeditions will be in the Arctic, at the research stations in the north. We also have, for high altitude physiology, we have a partner in Chile, one of the world's highest observatories, where we'll go and do some work with the communities and the workers in those environments. So mobility is important. This shows you a few pictures from the Kluane Lake Research Station. But essentially, the program provides mobility for graduate students compared to conventional training programs. Essentially, the students will embark on a rotation year, some of them, where they will spend time in multiple labs to get a sense of where the best environment for them will be. And trainees will also have opportunities to partake in capstone projects in living laboratories, in research stations, the Kluane Lake Research Station, and Alma in particular, and we're just another station in Europe. So we're very excited about our collaborative opportunities with ANA and its partners. So just a quick overview of the themes and teams. So what we've done is set up 6 themes, so cognition and behavior, neural imaging and mentoring, model systems, neural manipulation and modulation, data science, and brain, heart, and lung physiology. There's a focus here on education, professional skills, and mentorship. And we've identified team leads in all of these areas and our partners with the private, public, and industrial sectors. So you can see here we have a couple of collaborators from ANA, including its director, Mary Beth, and Rob, who just spoke before us. So why the Arctic? Well, we want to look at the physiological, psychological, and cognitive effects of co-specific interactions in remote environments, including physiological, emotional, and cognitive synchronization. We're interested in advancing our understanding and developing new ways to look at remote sensing and telehealth, and learning about and building research bridges with remote northern communities. So these are some of the partners that we wish to explore partnerships further with. There are just a number of them, but the Arctic Rangers, the Kluane First Nations, Inuit Regional Corporation, and the Polar Continental Shelf Program, and the government of the Northwest Territories. This shows you the governance chart of the program. We have an international program advisory board, an executive program governing committee, a management committee, and the outcome, which is the training of HQP. And this shows you here some of the flow chart through the different parts of the program. So with that, I would just like to thank you and be happy to chat more about this exciting opportunities. The program is new. We want it to be broad. We want it to be inclusive, and we're looking for many people to join and take part. The strength and the richness of the program is its interdisciplinary nature, and we think we have a great opportunity ahead of us with helping advance science in the North. Thank you.
And thank you, Marc. Yeah, that's very exciting. And lots of great opportunities coming up here. So, and our last speaker of this session will be Doug Chiperzak. He's just going to give a quick talk about a upcoming conference. Doug is a senior fisheries biologist with Stantec, and he's on the board of the Coastal Zone Canada Association.
I'd like to thank the Arctic Institute of North America for giving me the opportunity to kind of promote our conference, Coastal Zone Canada Association Conference, and which will be in Iqaluit in 2020. What first I'll do is just give you a brief introduction, and I'm going to be about 5 minutes here, and then we can have lunch. And so Coastal Zone Canada Association is a non-profit society. It was incorporated in 1993, and we had three kind of main objectives: promoting the understanding and appreciation and awareness of the uniqueness and value of coastal areas of Canada, providing a forum, and that's what we do through these conferences, for the exchange of ideas and information, for the sustainable use and development of coastal areas in Canada, and accomplish them, again, by hosting meetings, organizing conferences, and generating documents. We also put out a newsletter now that comes out almost quarterly. And we're focused on the four coasts of Canada. And so there's the Pacific coast, the Atlantic coast, the Arctic coast, but also we consider the Great Lakes as well. So we've been holding conferences every 2 years for a number of years, and we try to go back and forth between the different coasts. The last one in the Arctic was in 2006, and we held it in Tuktoyaktuk, and we had a great showing there, and we had people from all parts of the circumpolar world attended. And so we're hoping the same thing. We're back in the Arctic in 2020 to hold a conference, the conference there. So the conference will be in Iqaluit, near the Iqaluit, and the theme is, and I'll probably make a real mess of this, but Kwajamaja Tukkadunik, planning and preparing for the future. And we're in the process right now of developing the sub-themes under that overarching theme. But we had, so we're holding a conference in the north. It was important to bring in some northern influence and interest and concerns and ideas about what the themes are and about just holding the conference in Iqaluit. So a couple of our board members went up to Iqaluit in May and had a meeting with 20 different organizations and both government, Inuit, and other organizations in the community of Iqaluit. And that's where we came up with the theme, and but also in that theme there was four kind of components or natural laws, and they're working for the common good, protecting all living things, maintaining balance, and continually planning and preparing for the future. And these are things, and I've been working in the Arctic for about 36, 37 years, and it's a common theme all through, and when you talk to people in the various communities. the communities are, you know, are always changing, and probably more so than ever. And there's a need and a concern by, you know, some elders that, you know, we need future leaders and people that can, you know, take ownership of their land and move things forward and learn how to adapt to a changing world sometimes. So one of the things too is at these conferences we always have a youth forum, and so that's a component as well that we have in these. And so we've been interacting with Nunavut Arctic College and Kids on Board and stuff like that, different organizations. So the conference thing, like I said, is planning and preparing for the future. It's the conference is, I always forget the date, June 14th to the 17th, 2020. So you got lots of time to prepare. It'll be held at the Frobisher Inn, and they have a conference center there. There's a second hotel being that will be open before our conference begins. And there's also a number of other hotels. So there's lots of accommodation available there. We're working with First Air, who flies up into Iqaluit to get a discounted rate on airfares for people going up to the conference, also getting discounted rates on hotels and those type of things. We'll have special events. We always have some tours and this type of thing with these conferences. And so we've organized already a tour to Sylvia Grinnell Park, a beautiful, beautiful area where the Sylvia Grinnell just feeds into Frobisher Bay. And new brew, there's a new brewery in Iqaluit opening up, and so we. Open. Pardon? It's already open. Oh, is that? Oh, good. You tried it? Good beer? Good, good. And so a tour of that, and plus we're arranging many other things. And so I have here, we'll be finalizing hopefully our themes or sub-themes in the next 4 weeks or so, and then putting out a call for papers shortly after that. So we're looking for all sorts. I got a poster up there, so we're looking for anybody that's interested in the Arctic, whether it's industry, whether it's academia, excuse me, government, angles, different organizations, and especially local organizations as well. So, so I'm hoping that people will be taking interest and look at our themes and prepare a paper. Also, we're looking for sponsorship. We're a nonprofit organization, so we're always looking for money. And running a conference in the Arctic is an expensive endeavor. We have Mealpar, who is collaborating with us on this and providing some funding for the conference as well. But I got a little letter here that if anybody is interested in partnering or sponsoring something, I'll leave a few copies out and people can grab one. And so after that, again, thank you very much for the opportunity, and enjoy the rest of the day, enjoy lunch.
And so who we're bringing up first is Sarah St Germain, and she is a graduate student, almost finished here. Big countdown of to her dissertation defense, and she is in the Department of Geography. So please welcome Sarah.
There you go. Perfect, thank you. Okay, so I'm Sarah St Germain, and I'm a PhD candidate in the Department of Geography. And today I'm going to be talking about how different sized superglacial streams develop over time on an Arctic glacier. So superglacial streams are channels that exist on the surface of a glacier during the summer season. They're a significant part of transport of meltwater on the glacier surface, and they play an important role in energy exchanges. They also control spatial and temporal patterns of surface-derived meltwater. And they also provide a link to the on-glacial and subglacial system. Superglacial streams form where the erosion of warmer water melts the ice at a faster rate than the sun melts the surface of the glacier. So if the rate of water erosion is greater than the rate of the surface melt, then the stream insizes. So I've created 3 different classifications that I use within this talk, and they are surface streams, insize streams, and canyons. So surface streams are wide and shallow channels with water almost at the same level as the glacier surface. Insize channels are deep and narrow, and they have water occupying less than half the channel. And then canyons have a small stream at the bottom and occupy much less than the rest of the actual volume of the canyon itself. So there have been a few fundamental studies done, but many of them are decades old, and they've mainly focused on discharge and meandering. And then there are a few recent exceptions, studies on the Greenland ice sheet, but most of them use remote sensing to map stream location. So in terms of what I'm going to talk about today, I'm going to talk about this glacier here, and it has 2 unique canyons incised into the surface, as well as a number of smaller streams. So canyons have not really been described within the literature in this sense, and the objective of this project is basically to determine how superglacial streams form different sized regions, so in terms of the surface streams, the incised streams, and the canyons. So my study was done on Bylot Island, which is in the Canadian Arctic archipelago and part of Sermillic National Park. Fountain Glacier is a small Arctic glacier about 16 kilometers long and is located on the southern side of Bylot Island. So this study basically focuses on 7 different streams. So there are the 2 canyons that are located on the south, the 2 medium-sized streams on the south, and then the 2 surface streams that are right in the middle. So in order to actually conduct this project, I was looking at stream development over time, so I wanted to create digital elevation models and orthophotos from different years. So what I did was I basically placed plastic targets on the glacier surface, used a high-precision GPS to get the center coordinates of the targets, and then I flew a drone with a camera attached over my study area. And basically with all of this data, I was able to create the digital elevation models and the orthophotos using a program called PhotoScan. So once I had orthophotos from basically 2010 to 2017, I was able to basically draw on the orthophotos the stream location in every single year. And then I was looking at things like stream width, stream depth, valley width, and sinuosity and slope. And I looked at these characteristics along every single stream for every single year over 20-meter intervals. And then I was able to look at the correlations between all of these stream characteristics. And then I also looked at solar radiation in relation to the stream banks, and I had a whole bunch of visual observations. So now I'll tell you a little bit about all of the streams that I was actually looking at. So these are 2 of the surface streams. This is Central Stream and Camp Stream. So these are the 2 smallest streams that were on the surface of the glacier. And as you can see from the images, they have very small meanders and they are relatively straight, particularly in these 2 areas right here. And that's because the streams actually travel through these really small, narrow crevasses. And you can also see that the streams basically change location over time. And this is because the water level is so close to the adjacent glacier surface that the water actually jumps the banks on a frequent basis. And then the channel has to start a totally new path. And this happens on an almost yearly basis. So these are two of the incised streams. So I should mention that in these areas here, the glacier surface basically dips down, and it's an extremely steep region. So in these really sloped areas, the meandering was much greater, the incision of the stream was much greater, and that also had an increase in the bank width. And then there were a few unique aspects to these streams where there were cutoffs in a number of locations, and then there was a snow plug here. So in 2009, this was the channel, and then in 2010, it totally diverted. And then these are the last the two large canyons. So these streams had the largest watersheds and the largest discharge, and the streams were confined to the actual valleys, so they could no longer jump out of the valley because they were confined within it. And then solar radiation, which I'll talk about in a minute, had a large impact, and there were a number of cutoffs in all of the red areas. And in these regions, the cutoffs were formed by either crevasses or snow plugs. So solar radiation actually had a large impact on the valley walls and basically the angles that they were at. So in this picture, you can see that in Canyon 1, the wall angles are basically at an 80 to 90 degree angle on one side, and then on the south-facing side, it's at a 50 degree angle. And that's simply due to the solar radiation angle of the sun. And same with rock stream, just a little bit less significant. So this is another interesting finding that I came up with. Basically, cutoffs occurred in the canyon streams and the incised streams. So most likely occurred because of high discharge and high slope, which increased the sinuosity, which created the cutoffs. But in the areas with cutoffs, the actual profile of the valley was much larger than right adjacent beside it. And it actually formed like a trapezoidal type shape instead of a V shape. So basically, some major findings. Surface streams form in areas of low discharge and slope. The water frequently jumps the banks and the channels divert. And crevasses also have a large impact. In terms of the incised streams, they form in locations with high discharge or slope, which increases the meandering and the incision. And solar radiation had a large impact. And as you can see here, this was the snow plug that caused the channel diversion early in the year in 2009. And then in terms of canyon formation, the cutoffs were created by crevasses, so you can see that here, and snow plugs. So basically this snow plug was caused from snow avalanching off the 90-degree wall and onto the channel, which caused a different cutoff. And again, solar radiation had a large impact on the canyons. So conclusions. In terms of actually understanding superglacial stream, visual observations are extremely important. Solar radiation, crevasses, cutoffs, and snow plugs all impact the streams, and there's a large relationship between watershed area, discharge, slope, sinuosity, valley depth, and valley width. Thank you.
To our final presenter for the day, we've got John Yackel from, or is it Yackel? Yackel. I've only known each other, 10 years or so, but, professor in the Department of Geography as well, and he's going to wrap us up here for the day.
I wanted to sort of maybe end off on a little bit of an optimistic note today. And I think this particular project that's been alluded to a couple of times this morning already maybe does that for us. And I think it's maybe obvious from what they said in the video there is that there's tremendous international cooperation in what is taking place, started just 10 days ago, the largest ever Arctic Ocean expedition into the central Arctic Ocean. And I guess what I would like to share with this group is the University of Calgary and the Department of Geography's role in that expedition. So yeah, as was kind of highlighted in the video, we're talking about a very large expedition in excess of 140 million euros that involves multiple icebreakers, aircraft support, helicopters, 60 different institutions, 17, I actually have heard 19 countries, and more than 600 investigators and highly qualified personnel over 6 different legs spanning the entire annual cycle. And I think I'll flip to the next slide that sort of shows us. This slide has already been brought up. And what's really interesting about it is the fact that a number of distributed ice camps will be put out onto the ice near the German icebreaker Polar Stern, in which will act as sort of a hotel, if you will, for the various scientists on board. Perhaps maybe at this time I'll just sort of mention while we're talking about icebreaker support, and maybe it links to Rob Hubert's talk this morning when he was talking about the United States, Russia, and China. Very interestingly, the Germans have, in this particular project, partnered with the Russians and the Chinese for that icebreaker support. So it's and Rob and I were talking earlier today. On one hand, it's I think maybe a bit tokenism, a little bit or a little bit just symbolic of having those two particular countries support this collaborative international project with icebreakers, but their participation is needed and incorporated into the project nonetheless. So so here's another again schematic or cartoon, if you will, showing the various kinds of science activities that will be taking place. So as was mentioned before, and Brent mentioned this earlier this morning, looking at the sort of the coupled atmosphere, ocean, ice environment through the entire year, biogeochemical cycles, to looking at the smallest things like viruses to whales, and how they interact with the environment. So lots of instruments involved, lots of people involved throughout it. Beginning just 10 days ago, the Polar Stern has 40 scientists and 40 crew on board, and that amount of people on the ship will be recycled every 2 months, but there'll always be 80 people on the ship. So there's a tremendous number of people involved in the various legs conducting science. And so those are the expedition partners. And you can see Canada is one of those 19 nations listed there. And on the side you can see the University of Calgary, Manitoba, and University of Victoria. So I'm very proud to say that there's only 3 Canadians on this expedition, and the 3 Canadians, 2 of them are currently here at in the Department of Geography, a postdoctoral researcher and a PhD student under my supervision. And well, he's transitioning to the University of Manitoba. That's why you see Manitoba there. And then the other Canadian is a former PhD student of mine who's currently an associate professor at the University of Victoria, and that's Randall Shrine. So that's really exciting, and I'm very proud to say that that we have here at the University of Calgary the Canadian contribution to this project. So here are the icebreaker support and the timeline for the project, and it's as I mentioned, it was very interesting to hear Rob's talk this morning. You can see in leg 2 we have the Russian icebreaker support that will bring people and fuel to the Polar Stern once it makes its way into the central pack ice. And then on the far right is the Chinese icebreaker that's supporting the project as well. So when the Germans do projects, they do them big. And those are just the pictures of the 3 Calgary-linked individuals that will be participating on the various legs. I won't give you the boring details of our particular project. We're doing electromagnetics with remote sensing equipment, and we're studying the snow, but we're just one very small part of a very much larger project. I don't know if this is going to connect. If that first video was any indication, this is probably not going to work. I will just try to click this link and see if it opens up. I'm not expecting much. So I think what I might do is just, there it is, kind of starting up. Okay. I can't see that here, so I have no idea what to click next. But if you click English, and you'll see a map that comes up, and you can actually follow this expedition online, daily log postings to the website. I think it's okay because we're out of time, but yeah. Well, you can try. I think Mary Beth showed a picture of it this morning. You can actually see the current location of the Polar Stern, and a little blog note for the day. Shows you how far that the Polar Stern has traveled since leaving Tromsø, Norway, just last week. Okay, I can see that now. Great, thank you very much. Just close that window when you're done. Thank you. Okay, so here we are, real time. The ship has traveled almost 3,000 kilometers from Tromsø, Norway in the last week. And you can see the outline barely in white there where the pack ice currently exists. And so you can see that the Polar Stern is getting ready to enter the pack and find a flow to anchor to, and then start drifting. Turn its engines off, leave them in idle and start drifting with the ice pack, and the various camps out and about away from the polar stern will start to be set up. So I think my 10 minutes are up, and if you have any questions, we can talk offline about this experiment. Yeah, thanks very much.
Thank you, John. So this concludes our presentations, and I'm going to ask Dr. Murray to come back up and maybe sort of bring it all together, wrap it up. And I want to just thank everybody for participating, and I hope you enjoyed the event. And thank you to our audio and visual technicians, Andy and Devin. And also thank you to MacEwan Student Center for, the ballroom looks great with the renovations and everything. So thank you, and I'll let Mary Beth wrap it up.
So I'd like to thank all of you for coming today. I think that it's been a very interesting day, and for those of you who don't often come to the University of Calgary, there's some unfamiliar faces out there, I think you should know that this is only a small slice of the Arctic work that we do here at this institution, and only an even smaller slice of the partnerships that we have both in Canada and around the world, and that our students and our faculty are doing amazing and interesting work across a whole host of disciplines. And we're happy to have new people come here like Dan, and we're happy to see our graduate students like John's go out into the world and hopefully, make a change for the better. I also want to end on an optimistic note, and I'd like to do that first by once again thanking Melanie, who I have to say, without Melanie, this wouldn't have happened. Without Melanie, nothing would happen in our little institute. And I also want to thank the staff and the postdocs at ANA. They really make, we're tiny. Sometimes we're 11 on like in a really good 6-month period. There's 11 of us. Often there's 9. Sometimes it feels like there's maybe just me and Melanie. But we are punching above our weight, and it's largely due to our really great staff and our really smart postdocs. And I want to acknowledge them for making our presence on the national landscape something that is actually a presence as opposed to just a memory. And that's really important. And so to that end, and I can't believe I'm going to say this, but I do think we might think about making this an annual event where we can highlight the accomplishments and achievements of our students and our faculty at this university, and bring our partners in, whether they're coming from Inuvik or downtown or somewhere else. And we have a lot of international scholars that come to visit here that are working on Arctic issues, and we have a regular speaker series, and we try to highlight those. So I would encourage you to come out, and if you're not going to stay and have a drink and a snack, then I encourage you to go downtown and get outside and get in the streets with all the young people that are out there. Thank you.